Resuming our lecture now on section 1.6, we're going to talk about logarithms. And this again should be review. Most of you I think have seen, if not all of you have seen logarithms and work with them a little bit. But we'll take a little review of what those things were and kind of remind ourselves what we're talking about when we're talking about logarithms. When we talk about the word logarithm, all it means is it means exponent. So what we're doing is we're basically taking an exponential expression and putting the emphasis on the exponent. An exponential expression, something like this: 2 cubed is equal to 8. I think you all agree that's true. And we normally say that 2 to the third power is equal to 8. But I can say it a little bit different way and put the emphasis on the exponent by saying that the exponent on 2 to get 8 is 3. That's also a true statement, but again, I'm putting the emphasis here on the exponent. Now remember that when we had an exponential expression, the thing that was being raised to a power was called the base of that exponential expression. And so what we're going to do then is rewrite this exponential expression, only we're going to do it with logarithms, which again mean exponent, by putting the emphasis on the exponent. So we'll say the same thing, that 2 to the third is 8. In other words, the exponent on 2 to get 8 is 3, by saying the log, the exponent, on 2, my base of 2, but in logarithm form I write it as a subscript. The log base 2 of 8 is 3. The exponent on 2 to get 8 is 3. These two things say exactly the same thing. They just say it in a little bit different way. With that in mind now, we can talk a little bit more about logarithms in the context of this section, namely inverse functions. And consider the function f of x equals 2 to the x. That's an exponential function. Remember, an exponential function is a function where the variable is in the exponent and our base is something positive. Well, it turns out then that f inverse of x is going to be the log base 2 of x. It's going to be the logarithmic function. So this is, we would say that this is the log function base 2. And again, we can think about that in the context of the functions and logarithmic functions. Let's look at a couple of values here, maybe 0, 1, and 2, and where the function f of x sends these things. So what does f of x do? F of x takes the number and raises it to that power. So 0 is going to be sent to 2 to the 0 power. 2 to the 0 power is equal to 1. 1 is going to be sent to 2 to the first power. 2 to the first power is 2. And 2 is going to be sent to 2 to the second power, which is 4. So you can see here that this just says that f of 0 rather, is 2 to the 0, which is 1. F of 1 is 2. F of 2 is 4. Well, let's look at the logarithmic functions here and how the log function returns these values to the original. Well, if we take the inverse function, f inverse of 1, according to our formula for the inverse, that's the log base 2 of 1. That's saying, what's the exponent that I raised 2 to get 1? Well, the exponent on 2 to get 1 is going to be 0, precisely because 2 to the 0 is 1. How about the inverse of 2 in this function? Well, that's the log base 2 of 2. That's saying, what exponent do I raise 2 to get 2? Well, if you want to raise 2 to a power to get 2, you should raise that to the first power. So again, this is saying that this is 2 to the first is equal to 2, and so this is equal to 1. Finally, the inverse of 4 is the log base 2 of 4. That's going to be 2. What exponent do I raise 2 to get 4? That's 2, because 2 squared is equal to 4. So my inverse function returns things back to the original. And that brings up an important point that we didn't mention in 1.6 Lecture A. And that point is that if f and f inverse are in fact inverse functions, then it's going to be the case that f composed with f inverse of a value x will just equal x. Remember what composition means. This says that f of f inverse of x is equal to x. In the same way, we can make two cases here. The same way f inverse composed with f of x gives me back just the value I started with. F inverse of f of x is equal to x. And we can see that's true. You can check that with some of the examples we did in the first lecture of 1.6. Let's verify it with our example that we just looked at. F of x equals 2 to the x. F inverse of x is equal to the log base 2 of x. And you can see then if I were to take f composed with f inverse, say, of 8, I should get 8 back out. Well, this is f of f inverse of 8. Now, what is f inverse in this example? It is the log base 2 of 8. So I'm taking f of the log base 2 of 8. Now, remember how you read that. That's the exponent on 2 to get 8. Well, that's equal to 3, so that's f of 3. What is f? Well, f takes 2 to the power that you put into it. 2 cubed is 8. So I get back what I started with. Let's look at the opposite composition. We have to say both compositions because remember that composition is not a commutative operation. So what if we take f inverse composed with f, say, of 2? Well, that's going to be f inverse of f of 2. F says to take 2 to the second power, so that's going to be f inverse of 2 squared, which is f inverse of 4. F inverse says a log base 2, so this is a log base 2 of 4. That's the exponent on 2 to get 4, which is 2. Again, we end up with the same thing we started with. So compositions of a function and its inverse always give me back the exact same thing I started with. And we saw it's true for particular numbers here, but it's also going to be true in general. And that is to say that if f of x is equal to a to the x, then the inverse function f inverse is going to be the log base a to the x. And we have two important properties then that come from that composition, and the fact that the composition of two functions is a composition that gives us back x. If we take f composed with f inverse of x, that's f of f inverse of x. This is all just in very general terms here for any exponential function and any logarithmic function base a. What do we get? F of the log base a of x. Well, f says to take whatever you put into it and raise a to that power. So that's a raised to the log base a of x. That has to give me back just x, according to what we just said about the properties of a function and its inverse. But if you think about it, that makes sense. It's a little bit hard to think about. I'm raising a to a power. What's the power that I'm raising a to? Well, it's the exponent on a to get x. So I'm raising a to the exponent that I raise a to get x. So I get x. How about the opposite direction? How about if we do f inverse composed with f of x for any general exponential function and its inverse logarithm? Here we're doing f inverse of f of x. That's f inverse of a to the x, which is equal to, well, the log base a of a to the x. Well, this is just going to be x, and that makes sense because the exponent on a to get a to the x, well, that's x. What power should I raise a to if I'd like a to the x power? Well, I should raise a to the x power if I'd like to get a to the x power. So it all makes sense. Next thing we want to do is talk about some of the properties of logarithms. So the properties of logarithms, there's a couple of them listed, actually three that we're going to talk about mainly on page 68. The first one is that if I take the log of any base of two things multiplied together, I can split that up as the log base a of x plus the log base a of y. So I can write that as two separate logs. The second property says if I take the log of any base of one thing, one quantity divided by another, I can split that up with subtraction. Log base a of x minus the log base a of y. And again, I think you've seen all these properties before. Finally, the log base a of something to a power, say x to the r power. Well, I can think of that as, well, let's see, what is that? Let's kind of justify this one a little bit. That's x times x, r times. And so what I could do, according to property 1, is I could say that's the log base a of x plus the log base a of x, and so on, r times. But how many of those do I have? Then I have r log base a of x. So I have r times the log base a of x. The point is that this exponent here, the log of something to a power, you can bring that power down in front. So log base a of x to the r is equal to r times the log base a of x. And I'm going to squeeze in an additional property here that, well, I think it's a pretty obvious property, but it's worth mentioning. The log base a of 1. Well, what's that going to be? That's always going to be 0. No matter what our base is, the log of 1 is always going to be 0. Okay, and now let's look at graphically the two functions, the exponential function a to the x and the logarithmic function. Let's go ahead and look at these two formulas, y equals 10 to the x and y equals the log base 10 of x. The log base 10 is called the common log, and you can normally write that without the base involved, so we can just write that as the log of x. Now remember that these two are inverse functions of each other, and remember what that means graphically. If two functions are inverses of each other, then their graphs are going to be reflections across the line y equals x. Let's verify that, and let's go ahead and put in these functions. Okay, so there's 10 to the x, an exponential function that we talked about increases. Notice that we're at the point 0, 1, since 10 to the 0 is 1. And now let's go ahead and put in the log of x. And there you can see it's a mirror image over that line of y equals x. The reflection over that line of y equals x. Okay, now another thing you want to notice, remember that we said the log base 10, or log base anything, of 1 is equal to 0. So notice our log function at x equals 1 goes through 0. The other thing you need to notice is that, remember, with the function and its inverse, the role of domain and range is switched. Notice that, we come back here, for y equals 10 to the x, the domain is equal to all of r, and the range, you'll notice, is 0 to infinity. If you look at that function, there's 10 to the x, and that's going to be true for any a to the x power. The domain is all real numbers, but the range is just positive numbers. You can't ever take 10 to a power and get it to come out to be 0. You can get close to 0, but you can't ever get there. Well, that means then that for the log of x, our domain is going to be, well, it's going to be the opposite. They're switching the role of domain and range here. When we take a function in its inverse, the range is going to be all real numbers. That makes sense looking at the graph. You can see the domain, the only values for which it's defined, are 0 on out to infinity. The range, however, we can go down as far as we want to negative infinity, and this will go up as high as we want towards positive infinity. What that means for us is that we cannot take the log of 0 or a negative number. It is undefined. You can try it if you have a calculator with the log button. Go ahead and try and take the log of 0 or the log of a negative. It'll kick back an error message to you. Alright, then we want to talk about a special logarithm called the natural logarithm. The natural logarithm is the log with a base of e, the log base e of x, and the way we're going to normally write that is ln of x. Now, if you don't like that notation, you're not crazy about ln, you can always convert it back to the log base e of x. But notice that this is the inverse of the function y equals e to the x, because again, the base e in our exponential gives us an inverse of the log base e for our inverse function. So remember that our rules for composition, since these are inverses, says that the natural log of e to the x, well, that's the log base e of e to the x, if you like to write it like that, if you're not crazy about that new notation just yet. That's the exponent on e to get e to the x. Well, that's going to be x. Similarly, if we take e and raise it to the natural log of x power, or take e to the log base e of x power, that's e raised to a power. It's the exponent on e to get x. So it means raising e to the power, I raise it 2 to get x. And I see that I get x. Okay, so we have those two properties, and also remember that the log of e then is going to be equal to 1. The natural log of e is going to be equal to 1 simply because e to the first is equal to e. And this says, what's the exponent on e to get e to the first, or to get e? Well, I should raise e to the first power if I want to get e to the first power. Alright, the last topic then in this section is the change of base formula. We'll talk about this briefly, and then we'll put some examples on a third video. You'll notice on your calculator, if you have one, a scientific calculator, that there's only two logarithmic buttons. One is the log button, which is, as we said, the common log. That's the log base 10. And then you also probably have a button, the natural log, which again is the natural log of x, or the log base e of x. Well, what if you want to find the log base 2 of a number, or the log base 7 of a number? Well, you're going to use what's called the change of base formula, which says that if I take the log base a of x, I can rewrite that as either the common log of x over the common log base 10 of a, or if you like, the natural log of x over the natural log of a. Let's look at an example real quick of that. Let's say I wanted to find the log base 3 of 7. Now, what are we trying to find here? We're trying to find the thing that I raised 3 to get 7. Well, it's going to be somewhere between 1 and 2, right? 3 to the first power is 3, and 3 to the second power is 9. So I should get something between 1 and 7. Well, I don't, or between 1 and 2. I don't have a log base 3 button on my calculator, but I do have a log base 10. So I could write this as the log of 7 over the log of 3. And go ahead and put that in your calculator if you like. If you're not crazy about your log base 10 button, you can use your natural log button. Sorry about that. Natural log of 7 over the natural log of 3. Either way you do it, you should get rounded to a couple of decimal places here. Let me do it here myself. About 1.77. And again, that makes sense, as we said, something between 1 and 2 to give us an output of 7. Since 3 to the first is 3, 3 squared is 9. So there's the change of base formula that you can use if you need to use your calculator to find a the value of a logarithm that has a base other than 10 or e. Okay, that's going to be it for this video. It's getting kind of long. Let's do some more examples in the next video, some more examples of some of the problems dealing with the logarithms and natural logarithms.